All right, going to talk about acids and bases, the basics. Yes, that's a pun there. All right. Acids and bases are extensively studied. There's an entire field of chemistry dedicated to the study of acids and bases. So in 15 minutes, I'm not going to teach you everything that you need to know about acids and bases, but I am going to give you an introduction, the basics of what acids and bases are. Okay? First, definitions, because we always got to start with definitions, so we got to define what's going on. The first definition, did I spell his name right? The Arrhenius definition. Just double checking. Yes, I did. All right. So that's Arrhenius' definition. What Arrhenius noted is that when you put solutions into water, some generate H plus and some generate OH minus. So Arrhenius acids generate H plus. What we all now consider to be H3O plus. Okay? There's still some debate in the scientific field about whether or not it's a free proton H plus or H3O plus. Most people think it's H3O plus. Some people still think it's H plus. They fight, they're like rival gangs in chemistry, It's like a West Side Story. They do a little dance and they're complaining about H's and H3O pluses. So some organic chemists, I'm like, I don't care. They're all Lewis bases and Lewis acids. And then they start attacking me. It's terrible. I've been beaten up many times in the American Chemical Society conferences. Please don't make me go back. All right. Ha ha ha. This is why you watch the videos, for all the funnies. Arrhenius bases. An Arrhenius base generates OH inside of a solution. All right. Did everybody have that committed to memory? Are you nodding at your screen? Good. Now, forget it, because these definitions are old and generally not prescribed to. A guy named Bronsted came up with a better idea, and he is much better at it because he's got a zero in the middle of his name. Bronsted, where's the zero, Dr. Elaine? Right there, Bronsted. Bronsted came up with a better definition, and he said that when you put a species in a solution and it donates H plus to the solution, it's considered an acid. Right? So it's an H plus or proton donor. Okay? That means it gives up H plus to the solution. Similarly, for Bronsted bases, the Bronsted base is an H plus acceptor. Right. Notice that this one doesn't have anything to do with OH minus. It just says that it's going to absorb H plus in the solution. Okay? There's two other definitions that we're going to use. Depending upon the text that you're using, you may or may not see this. But I love them because I'm an organic chemist. I mentioned at the beginning of the video. So I feel obligated to mention Lewis acids and Lewis bases. Right? The Lewis acid accepts electrons. And a Lewis base donates electrons. So it's kind of the opposite of what you get with Bronsted, but instead of H plus, we talk about electrons. All right, so there you go. There are some definitions for you about acids and bases. The important one, or important ones, are going to be this one. I'll put number 1 next to it, because for our definition and our discussion right now, we'll talk more about Bronsted acids. But what I'll do is I'll write number 2 here as well. Okay, and I'll do that in black so you can see what's going on. If I write Lewis acid, you'll see La here, and that represents a Lewis acid. And a Lewis base I'll also represent there as well. If you have a fundamental grasp of Lewis acids and Lewis bases, organic chemistry actually becomes a lot easier, which is why I talk about it. So let's talk about some strong acid, strong base systems and see how they work in association with water. Okay, now I put these up here. Bronsted acid, Bronsted base, Lewis acid, Lewis base. Bronsteds are going to be in purple, Lewis's are going to be in black. So you can see kind of what's going on in these examples. All right? So the first we're going to talk about something simple. Hydrogen chloride dissolved in water. What's going to happen to it? So this is a gas. This is a liquid. What's going to happen when these two things are put into solution? Well, over here I'm going to have H3O plus and Cl minus. Both of these are going to be considered aqueous, which means that they have dissolved in water. We know that this is a strong acid, so I'll represent that using equilibrium arrows. Okay? So a strong acid is going to dissolve quite readily inside of water. Now what happens here? Which one of these two reacting species, where my head is, which one of these two, of these reacting species, is going to be considered a Bronsted acid or a Bronsted base? Right? Which one of these is donating the hydrogen? This one, right? This hydrogen jumps ship and goes to that water to become H3O plus. So this is what we're going to be considering a Bronsted acid. Now, you can't have your yin without your yang. So if I have a Bronsted acid, I've got to have a Bronsted base. Okay? In this case, water, strangely enough, is going to be my Bronsted base. Okay? Every side of the reaction has a Bronsted acid and a Bronsted base. So over here, which one of these is the Bronsted acid and which one's the Bronsted base? Which one is going to donate its hydrogen? Well, if I go backwards this way, I lose a hydrogen from H3O plus to become H2O plus. So on this side, H3O plus is my Bronsted acid, and Cl minus is my Bronsted base. Okay? I know it's a little confusing, but you have to recognize that every side in an equilibrium, because two reactions are going on, every side is going to be considered to have a Bronsted acid and a Bronsted base. Okay? I'm going to save you that confusion right now and just say, just focus right now on what's going on with the reactants. Now some of you are looking at this and saying, all right, that makes sense so far, but how does that hydrogen really get over to the water? It involves the flow of electrons. So I have to draw the proper Lewis dot structure of water. Okay, so here's water, dot, 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 and I've got a Cl and an H. Okay? So now the electrons have to transfer to the hydrogen. So these electrons, and I haven't used red yet, so I'll use red. These electrons, where's it goes right under the projector? These electrons are going to move directly to that H. And in doing so, what they're going to do is push electrons from that H to that chlorine. Okay? So as a result, what we have in the system is the generation of H3O plus and Cl minus. Let me put the lone pair on there. Okay. If we look at it this way, we have to define it kind of what's a Lewis acid and what's a Lewis base. Which one accepted the electrons? That's the Lewis acid definition. Well, this hydrogen here accepted the electrons, so that's our Lewis acid. This one donated its electrons, so as a result, that's the Lewis base. Both of these align as to tell us which one's a Lewis acid and which one's a Lewis base. Okay? Pretty simple example here, so I'm going to make it a little bit more complicated and we'll see what happens. In this case, I've got acetic acid, right? And what happens with this one? Notice in this case, I've got the equilibrium arrow, and it's shifted a little bit because, as we discussed before, acetic acid is not a strong electrolyte. It's a weak electrolyte. Because it's weak, it doesn't completely dissociate when it hits water. So it's going to be mostly this thing, okay? Now, does that affect whether it's a Lewis acid or a Lewis base? Now, I'll let you decide. Its name is acetic acid. So what do you think? Is it an acid or a base? Don't say base. You're being a smarty pants. It's not a base. It's an acid, right? Okay, so this one is considered a Bronsted acid. And again, water is considered our Bronsted base. Now this is a pattern that we get through a lot of acid-base type chemistry, right? What is our Lewis acid and our Lewis base here? Well, if you look at it, water kind of does the same thing that it did before. And I'm not going to draw it separately here. Okay, water has that lone pair of electrons. These electrons flow, okay, and they go into this molecule, and they generate what's going on over there. So, what do I have? Since this accepted electrons, it's considered a Lewis acid. And since this one donated them, it's considered a Lewis base. Okay? Now there are some cases where you can have a Lewis acid, but it can't be a Bronsted acid. Right? But all Lewis bases and Bronsted bases generally, for the most part, are going to be synonymous. Okay? So let's see that example with the Lewis acids. All right. Now this is an example. And which one of these is going to be the Bronsted acid? Well, you look at this one and you say, well, this one can't be a Bronsted acid because it's not giving up any hydrogens. So you look at this and say, well, this one's got hydrogens, it must be a Bronsted acid. Well, it's not. Because if you remember about the polarity of the molecules, okay, carbon and hydrogen, their electronegativity is very similar. So when they're that similar, there's not going to be a polar index. And as a result, there's no dipole. That means that they're not going to come off that carbon. Okay? So since these hydrogens aren't coming off the carbon, I don't have anything that donates hydrogens. So I can't have a Bronsted acid at this point. But what about this thing and electrons? Well, boron has 6 electrons. My ether, diethyl ether here, has some extra electrons on that oxygen. So what happens is I get a transfer of electrons from that oxygen to that boron. And I get a molecule that looks like this. And I'm not going to draw lone pairs around the boron. Okay, now I've got that structure. What's the formal charge on the boron? Boron normally has 3 valence electrons. I've got 1, 2, 3, and a 4th bond. So boron is negative. What's that going to be in the oxygen? If you remember the rules, if oxygen's got 3 bonds, oxygen's in a lone pair, oxygen is going to be positive. All right? So this particular structure involved a transfer of electrons. Since this donated electrons over this way, it's considered a Lewis base. And since this one accepted electrons, it's a Lewis acid. But they're not Bronsted acids or Bronsted bases because there's no hydrogens to give or accept. Okay? So as a result, I can have Lewis acids and Lewis bases without hydrogens, but I can't have Bronsted acids and Bronsted bases without hydrogens either. Okay? One more thing I want to talk about with this, and that is going to be polyprotic acids. Now what does that mean? Polyproton. That's got multiple hydrogens on there. Not that it has a lot of hydrogens or a lot of protons, because anything that's not hydrogen is going to have more than one hydrogen or more than one proton. It's going to be a polyprotic system, which means I'm going to have more than one H plus donated by the system. So this is sulfuric acid. And if you've watched any sort of movie that's got sulfuric acid in it, you know that people that get acid thrown on them start smoking and screaming, right? I've got sulfuric acid dumped on me before. I haven't started smoking and screaming, okay? I did get out of my clothes quite fast, right? And rinse my body with that, but I didn't start screaming or anything like that. Not really what happens, okay? You'd have to wait a while to see the effects of that. But for polyprotic systems, it just means that I've got more than one hydrogen to give up. So what happens in these systems is when I put these in the presence of water, I'm going to get H3O plus and HSO4 minus. Okay? Now HSO4 minus, also known as bisulfate, is a pretty good acid in its own right. So I put this in the presence of water, I get H3O plus. In this case, I get SO4 minus 2. Because I can give up 2 hydrogens there, it's considered a polyprotic acid. Now one thing you may want to note is that this is always a 2-step process. The first hydrogen here, and this goes the case for any polyprotic acid, the first hydrogen is going to be the easiest to come off. Okay? Matter of fact, this hydrogen that comes off of sulfuric acid puts it in the category of strong acids, because they get 2 ionic species. It's a very, very strong equilibrium. This one, however, because I've already got a negative charge here, is not so crazy about losing that sulfate. So this is considered a weak acid. Because it's a weak acid, it doesn't completely dissociate when it hits water. So there's not a lot of sulfate left over in the water system. However, there is going to be a lot of bisulfate in that water system. Okay? So polyprotics, all they are just acids that give up more than 1 hydrogen. You should be aware of that.